But just real quick, first of all, definition. The notation sine inverse and the term arc sine, those mean the same thing. Exactly the same thing, the same function. Cosine inverse and arc cosine are also the same thing, and so are arctan and uh, tan inverse. Uh, so maybe I should put semicolon there. Tan inverse and arctan, etc. All right, so by definition, the thing about inverse of trig functions is trig functions are periodic. So they don't actually have, for something to be a function, it has to have only one value, only one output for every input, right? It can't have multiple outputs for a given input. So that's called the vertical line test. So so that's not a problem for sine and cosine, right? Of course, your sine function looks like this. Wrong color. So if this is my x, oops, again the wrong color. If this is my x, then if I were to graph sine x, it looks like this. This is fine. This passes the vertical line test. Right? There's no point where it overlaps, unless it's just because I'm bad at drawing. But to get the inverse, to get an inverse for the sine function, the inverse also has to pass the vertical line test. So the inverse to the sine function would look like this. It's basically what you get if you flip over the line y equals x. So if I, this is not quite dark enough for you to see it. If I flip over this line, to get the graph of the inverse, so then that gives me a graph that looks something like this. Oops. All right, let's see. It's going to start here. Okay, so that's going to be going basically the same direction, and then we're going to be going like this. So this is this is like the graph of arcsine, right? So you think, okay, is this the graph of arcsine, right? Because this is, in general, how you find the graph of the inverse of a function. You just flip over the line y equals x, and you've got the graph of the inverse. Problem is, this doesn't pass the vertical line test. So let me give myself more space, I guess. So this does not pass VLT. So it's not a function. So what we need to do then is restrict this this graph to being just a part of the graph that does pass the vertical line test, because we need arcsine and arc cosine, etc., to be functions to do anything useful with them at all. Otherwise, you know, you plug a value into them and you don't even get a single value as an output. So in this case, I'm going to restrict it to be right in here. This is the value of the arcsine. So this is arcsine. This is not arcsine. Arcsine is just the stuff between here and here. Now this curve just between here and here, that passes the vertical line test. So so that is what we take as our definition of the arcsine. So the upshot is that arcsine has to have range between minus pi over 2 and pi over 2. So remember, in your graph of the sine function, this is pi over 2 here. Maybe I should write that a different color. This here is minus pi over 2. So if I transplant those to this y-axis, what I've got is pi over 2 here and minus pi over 2 here. And I had the value, let's see, do orange maybe. I had the value 1 up here and minus 1 down here. So now that becomes minus 1 out here and 1 up here. So now this is what the arcsine looks like. So the domain is between minus 1 and 1, and the range is between minus pi over 2 and pi over 2. So arcsine has range between pi over 2, or minus pi over 2 and pi over 2. The reason that's a big deal is that if I ask you what the arcsine of some angle is, and you write pi, that's wrong. Or if I ask you what the arcsine of some number is, and you write pi, that's wrong because arcsine can never give you pi. It has to be between minus pi over 2 and pi over 2. So if you do the same thing with the graph of arc cosine, you get that it has to be between 0 and pi. So arc cosine can never be negative. I wish these numbers matched up. They don't. And arc tangent is even more frustrating. It goes between minus pi over 2 and pi over 2. The way I remember that is that tangent basically behaves like sine because tangent is sine over cosine. So the thing in the numerator kind of determines what it really does, and the thing in the denominator just scales it. Arc cosine, I don't know. Cosine is just weird. Cosine's the weird one. So sine between minus pi over 2 and pi over 2. Cosine's a little bit weird. I recommend you memorize these numbers. It's not like the most important thing you're going to need in this course, but occasionally it comes up. It's not just like limited to like this one beginning of the course or anything. We're going to keep doing stuff with arcsine every now and then until like the very end of this course, unfortunately. Right, so why are these the domains? Here's a not moving version of what I just told you. All right, so here's an example. I'll just do this one because we do need to move on, so I'll just do this one live. And rather than giving you time to work on it, I apologize, but I recommend practicing a couple of these if you've got time. All right, so I want to compute the arcsine of minus root 3 over 2. So the first thing I recall is that the domain is the domain of arcsine is equal to minus pi over 2 to pi over 2. So I only am interested in this part of the unit circle because that is the part of the unit circle between minus pi over 2 and pi over 2. So this domain is from this table right here. So I've drawn the relevant part of the unit circle now. And here's the other thing to know. Coordinates of, this is just a fact that follows from the definition of polar coordinates. The coordinates of any point on the unit circle are cosine of theta in the x-coordinate and sine of theta in the y-coordinate. where theta is the angle that the point makes with the x-axis. So what do I mean by that? Well, I guess I should really say the vector. So, all right, the angle that the corresponding vector makes with the x-axis. So if I've got some point, maybe up here, for example, I'll call that P. Then that gives me a corresponding vector. So it looks like that. Oops, wrong color. All right, and then I've got my angle theta that I should probably label the axis. That's the x-axis, that's the y-axis. So theta is the angle that the vector of that point makes with the x-axis. So then P would be equal to cosine of theta, sine of theta. And the same thing works if the point is down here, for example. So now what I do then is, because I know that this is the only part of the unit circle I'm interested in, sorry, let me color code a little bit more. I think it'll make things a bit clearer. All right. So from there, what I do is I'm just going to write all of the common angles on here and see if I can find one that matches up to the arcsine that I'm looking for. So I want arcsine. I want to find theta, which is equal to arcsine of minus root 3 over 2. Right, so I want to find the arcsine of minus root 3 over 2. That means that the sine of theta is equal to minus root 3 over 2. And theta is in between minus pi over 2 and pi over 2. So let me color code a little bit here. Theta, and then that we're going to look for right, the corresponding pink point. So we're looking for the corresponding, the pink point that corresponds to the y value minus root 3 over 2. So again, the problem is to evaluate this arcsine. So if we find theta, we're done, right? Because theta is equal to this arcsine. So now I'm just going to copy this whole chart. I'll delete some of the stuff that we don't need. Let's see. There we go. Got it. All right, so now I'm going to draw the common angles. So first of all, or the points corresponding to the common angles. Let me go ahead and actually make this a little bit bigger also. It's blocking my ratio. That's annoying. All right, so one point that's corresponding to a common angle is the point 1, 0. There's another one up here, which is 1 over root 2, or root 2 over 2 if you prefer, 1 over root 2. That would be a 45-degree angle. Then there's this one, and then there's going to be 3 down here, and then of course there's also these on the axes. So this will be 0, 1. This will be 0, minus 1. That's 1 over root 2. So this is 1 over root 2, minus 1 over root 2. This is going to be root 3 over 2, 1/2. This one is going to be 1/2, root 3 over 2. And this one is going to be, let's see, root 3 over 2. The x values are always positive because that's the part of the unit circle I'm looking at. So this would be root 3 over 2, 1/2. And then finally, I've got 1/2, this is negative, minus root 3 over 2. So the y values down here are negative because I'm below the y or the x-axis. I'm on the negative part of the y-axis. Y values up here are positive because I'm above the x-axis, right? This is the y-axis. And everything is on the right side of the y-axis, so all the x values are positive. So, all right, now I just need to find the one that corresponds to minus root 3 over 2. Sine is the y-coordinate. So that's this guy right here. And so now I can kind of draw my angle and reason through which one that must be. That'll be 60 degrees, right? 45 degrees would be this point here, 30 degrees would be this point here. So this is 60 degrees, or actually it's minus 60 degrees, sorry, because we always sweep out in a counterclockwise fashion. So this is minus 60 degrees, or minus pi over 3 radians. So that's how you do it. So ultimately we found that theta equals minus pi over 3. And that's the final answer.